So Fubini's theorem tells us that in order to calculate a double integral on a certain area A, we can calculate it as an iterated integral, which means that we can calculate it as an integral inside of another integral. Okay? So we can do first an integral along the x direction, and then we can do the result of this integral, which is a function of y only, because the x dependence has disappeared. We can do the integral along y. And that way we can do the iterated integral. And Fubini's theorem also tells us that we can swap the order. We can, instead of doing first the integral along x and then the integral along y, we can also do first the integral along y and then the integral along x, and the result will be the same. If a mathematician is watching this video, they might complain that it's not so simple. There are some conditions that the function must fulfill in order for this to be true. And that's fair. That's a fair criticism. So let me open up the Wikipedia page for Fubini's theorem, which is presumably written by a mathematician, hopefully. So Fubini's theorem is a result that gives conditions under which it is possible to compute a double integral by using an iterated integral. Okay, so Fubini's theorem actually gives you what are the conditions that allow you to do this. In practice for us, in all of the problems I will be doing in this module, these conditions are always fulfilled. Okay, the conditions are written here, and they are things like the integral not diverging and being well defined and so on. Okay, so very mathematical. It's a very mathematical result, and it's not trivial. But for us, let's only get the main message, which is that for the functions that we are used to integrating, we can change the double integral into an iterated integral. Okay. And in practice here, I'm doing it for a rectangular region. So for a rectangular region where x changes between a and b and y changes between c and d, this defines a rectangle. So this is our area of integration now. And then you notice that the way you write the iterated integral is that if you first integrate along x, you put the x inside of the parentheses, and then the limits of this integral symbol correspond to the integral along x. Okay, so how do you know that these limits correspond to x and not to y? Because dx is here. So this integral symbol is being closed by the dx here. So that tells you that this refers to x. So this is between x equals a and x equals b. And then outside you have dy, which is closing this integration symbol, which is telling you that the limits in y are changing from y equals c to y equals d. Okay? Or if you do the other way around, notice that I swapped dx and dy, but I also had to swap the limits. So now the inner limits, the limits corresponding to dy are c and d, which correspond to y, and the outer limits of the outer integral, which correspond to dx, are a and b. Okay? So if that is clear, we can jump straight into an example.